Hello, my name is Pierric Mora. I'm going to present you a work about the interaction of surface waves with an array of subwavelength resonators in a granular medium. And I will show you that such a device can be used to build a barrier with broadband performance. Let me start with some motivations. So in the context of seismic metamaterials, which are materials which have appeared in the last years as a new strategy to protect some regions of space from seismic waves, so waves rising from an earthquake, but also ground-borne noise, vibrations produced, for instance, from an infrastructure, a railway, factory. So what you see here are selected examples on works with a specific focus on works that rely on resonators because they can reach significant effects at subwavelength scales. And the last two examples deal with granular media, which adds quite a complexity because of the gradients and because of the wave propagation, which becomes more complex. But these gradients are representative of what really happens in sedimentary soils, so that if we want to build efficient metamaterials, we have to make them work. We have to understand how to make them work with such complexity. This is my experimental setup. You see a sandbox. You see here a shaker that I use as a point and a pulse source. And I can measure the surface vertical motion with a vibrometer, which can move along one axis. And this way I can measure and study the incidence, reflection, and transmission of surface wave through an array of resonators that you can see here. Actually, you see masses. I call them resonators. I explain you why soon. And this is the typical seismograph that I can measure. This is the result. I will come back later. But let me start with a background about the sand, about what granular medium is. You can view it as macroscopically as an elastic medium with elastic constants that depend on the applied pressure because of the micro contacts between grains and because of the friction. So when you take a half space, a pile, a heap of sand, what you have is an elastic medium with zero elasticity at the surface and increasing properties with depth. And this gradient has strong guiding properties. Let me compare it with spaces that you might be familiar with. The first one is a homogeneous half space, and you know that in this case, the only surface wave is the Rayleigh wave. And you may also know that if you add a slow layer, then you can have a multimodal, several modes, several surface waves by increasing the frequency. In our case, the gradient is peculiar in the sense that it doesn't have any length scale, so that at any given frequency, there is an infinite number of modes of propagating open channel. And this is a typical set of signals that you can measure. So this is time, this is space, and you see a lot of waves, a lot of modes, a lot of dispersion, a lot of velocities. And when you do dispersion analysis, you see that the surface motion is dominated by modes 1 and 2. These mode shapes are theoretical, and when you look at higher order modes, the one number 3, but it's qualitatively similar at higher modes, you see that these higher modes guide the energy in the depth. So to state more clearly my objectives are to stop, to efficiently affect modes 1 and 2 in order to protect the surface, having in mind that channels may be open in the depth. So one word about the scatterers, which I called resonators. Assume that you have an elastic half space and you push on it, and so the space reacts as a spring with a spring constant which depends on the shape you are pushing with. If you now push on the mass and release it, you have a mass, you have a spring, so you have a resonant mass spring system, and you expect the mass to move together or against the surface according to the frequency with such qualitative behavior. This is the transfer function, the Bode diagram of a resonant system. So what we expect is that the mass should effectively clamp the surface at high frequency after reaching resonance frequency. And just to set IDs, to have some orders of magnitude, if we take the mass I am using and put it into the constitutive of the granular medium and assume, of course it's not realistic, but just to fix IDs, assume that everything is homogeneous, we expect things to happen around a few hundred hertz, say 500. So now let's go more quantitative. Let's go to finite element modelings. And here I am modeling an infinite arrangements, periodic arrangements of masses of resonators to study the dispersion properties. The basic assumption I am making is that the granular medium consolidates only within this blue region, which is a pillar below the contact area. It's of course not what happens in reality. In reality, we expect something like a cone, but it turns out that this shape is not a critical parameter. So this is an acceptable approximation indeed. And what you have as dispersion that you can calculate this way. So in gray, you have the original dispersion curves. And here in color, the curves with scatterers. You see that with these onsets here, that modes 1 and 2 hybridize efficiently with a longitudinal and a vertical resonance. And if you look at higher frequency, at this inset here, you see that it's the net effect is effectively to clamp the surface. So now what does it mean in terms of transmission properties? I am now modeling a full-scale domain, full domain. I'm now putting one line, only one line of such scatterers, and still assuming that the consolidation is only within a pillar. And I can measure the surface displacement here and integrate it and measure this way the transmission ratio. And what I do is to play with the altitude, with the depth of the source in order to select one or the other mode. And if I choose appropriately the depth of the source, I can generate almost only mode number 1, here almost only mode number 2, and here almost only mode number 3. This is a frequency domain at these frequencies, so this region, and you see that modes 1 and 2 are efficiently blocked while mode number 3 goes through essentially. So what happens? What's the explanation? I've been talking a lot about clamping, and it's indeed an important ingredient, but does it explain everything? And the answer is no. You can do complementary numerical analysis by to measure the transmission from free to clamp half spaces, and if you don't put consolidation, there is a significant transmission. The reason is that, okay, you are blocking the surface displacement, but as soon as you have zero elasticity here, you can have a very significant displacement quite soon. So the transmission is quite high, actually. But if you now put some consolidation, this is without clamping, you see that the scale of the penetration changes. So that's when you combine both clamping and consolidation, you have a high modal mismatch, which results in a strong attenuation, well, a strong reflection. So now if we go back to the experimental data, this is the figure I showed you at the beginning. You can see that modes 1 and 2 are efficiently reflected, and if you do a dispersion analysis, you see a lot of reflection in modes 1 and 2, and you see that the transmission is mostly due to mode number 3. We can do better. We can go more quantitative with this data. Let me explain how I process it. First, I split the map into 2 maps: a map which contain the incident and reflected waves before the scatterers, and a map which contains all the transmitted waves after the scatterers. On each map, I do a modal selection in the Fourier space, and but this is not enough, because this way I cannot distinguish between 1-to-1 transmission and 2-to-1 conversion, for instance. So I have to do something more, and I have to select the appropriate time arrivals, and I do it after compensating the dispersion. In this way, I can select a transmission 1-to-1, 1-to-2, etc. And then I assemble the pieces and I can measure the transmission ratio by measuring the amplitude nearby the interaction. And most importantly, this processing is quite intrusive in terms of bias. So I have to do the same for reference set of data and divide it to dBias. And this is the results that we can obtain. So the left-hand part is for mode number 1 as the incident wave. This is for mode number 2 as the incident wave. And these are the transmission ratios. So these points stand for experiments. The dotted lines stand for theoretical numerical model with roots. You see that there is pretty good agreement, and you see that indeed there is a low pass filter like behavior. I have also plotted a numerical model without roots to see that the effect of the roots is to indeed reduce the quality factor, because without roots you see resonant effects that increase the effect. And finally, talking about wavelength scales, we do have subwavelengths. We do reach, say, -10 dB at lambda over 4 approximately. And if we are smart enough to reach the qualitative behavior of the model without roots, then we can reach theoretically -10 dB as soon as lambda over 15. So as conclusions, I have shown you how these devices, how these resonators can be used to build a low pass barrier that works for both modes 1 and 2 with a broadband and sub-wavelength performance. I have shown that the ingredients, the effects results in 2 ingredients. The first one is a boundary condition change, which is a dynamic effect. The second ingredient, important also, is that we should have consolidation. We should induce some consolidation. This is a static effect. If you do complementary numerical analysis, you can see that it is very important to block both longitudinal and vertical motions. Otherwise, you have a significant mode conversion and transmission at the surface. And yes, I also studied a bit. I don't have time anymore, but I also studied a bit the effect of the roots. It would be great to have a solution without roots. It would work better. So thank you for your attention. I can now answer the questions.